As we've seen in other units, we can apply transformations to create new polynomial functions. In 1a, we're asked, what cubic function do you obtain by applying the following transformations to y equals x cubed? A vertical stretch by a factor of 3 is going to result in a multiplier of 3. A reflection in the x-axis is going to be shown with a negative in front of that 3. A horizontal translation 5 units to the right means we need to apply that transformation before we square. And since it's horizontal, it's going to go with the opposite sign from what we would expect. And that's the polynomial. What cubic function do you obtain by applying the following transformations to y equals x cubed? A horizontal stretch by the factor of 2. Okay, we know that if it's going to stretch horizontally, it's going to be backwards from what we expect. So instead of multiplying by 2, we're actually going to multiply by a half, and it's going to happen inside the parentheses before the cube happens. Oh, this one's a cube, not a square. All right, and then here we have a vertical translation 5 units up, so that happens after the cube. And the only thing we would do to finish this off is, because there's arithmetic that we can simplify, we'd want to do that. So we're going to say y equals 1/8 x cubed plus 1/5. Notice, if we saw the equation written this way, we would have no way of knowing that that was a horizontal stretch by a factor of 2, which looks like 1/2 in the problem, rather than a vertical compression by a factor of 1/8. We wouldn't be able to tell the difference. Next, we have to realize that polynomials are actually a little bit more complicated than some of the other functions we've studied. In all of the other functions, linear, quadratic, absolute value, we can look at them and see that there are transformations that take the parent into the child. But with some polynomial functions, they are not the result of transformations, and there's actually other algebraic changes taking place. So if you have a cubic, for example, that looks like this, that is simply the result of a transformation. So it's going to be a cubic with like that wiggle in the middle, as opposed to big highs and lows. When we start seeing highs and lows like this one, that's the result of some more complicated algebra taking place and is not purely a parent function that's been transformed. This last one as well is the result of far more than just transformations. And you can sort of see that when you look at it in its factored form. In one place, x is being subtracted with a 3, which would suggest a horizontal translation to the right by 3. But then in another spot, it's x plus 2, would suggest a horizontal translation to the left of 2. We know that both of those things can't be happening at the same time, and so we can sort of come to understand that there's more algebra going on here. But there's actually something else interesting about this factored form. Notice x minus 3 is kind of like a linear factor, right? It only has a power of 1. Whereas this is a quadratic factor, and this one is a cubic factor because of those multiplicities thrown on there. And notice, if you look at different parts of the graph, it's almost like you see a cubic or a parabola. So for example, if I'm looking in here, that looks an awful lot like a cubic, and notice that x value is 1. So if I go look at the x value of -2, the 0 associated with that factor, notice it's almost like I have a parabola happening at the x value of 2. And then if I look at the x value of 3, which is what associated with that first factor, notice that is very steep. It's almost like that part is a line. So we can sort of look at this polynomial as being the product of other polynomials. And that's a little bit of a different way to think about these polynomials. It's not just straight transformations. Instead, it's the product of simpler polynomials. In quartics, we have the same distinction. Just like the cubics in first were just transformations, these quartics at first are just transformations. We can see that it's basically the same shape, and it's just been translated 2 to the left and 3 up to go from the child to the parent. Whereas again, in the second problem where we start to see more pronounced rises and falls, these highs and lows, these are the results of greater algebraic changes than just transformations. Now, taking a look, we're asked what are all the real zeros of y equals 1/2 x minus 2 cubed minus 3? Okay, so an important thing to realize here is this is a transformed cubic. So we should expect it to basically look like this, but it's been vertically compressed, it's been translated 2 spaces to the right, and it's been translated 3 spaces up. So if I think about that, if this thing went 2 spaces to the right and 3 spaces up, the axes must be around here somewhere. So when I'm looking at this and I'm being asked about real zeros, I should only expect to see one of them happening. Now I can't obviously tell what that one is by looking at this particular form of the equation. I could multiply it out and then maybe try P's and Q's, but we've got a little hint here that tells us to take a peek at the graph with the calculator. So let's grab our graphing calculator and do that. Oh, just a minute. Before I tell you to look at the graphing calculator, notice I translated that up. I must have lost my mind. That's going to translate down because the y translations go in the exact direction you would expect them to. So we're going to see something that looks more like that to be a little bit more accurate. So let's go ahead and take a look at our graph. So when we do this, we're going to type our equation in exactly the way we see it on our paper. And we can just use a zoom standard and we'll see that this looks basically like we expected it to. Translated to the right and down, and it's a little bit more flattened vertically than it would have been otherwise. So that's a transformed polynomial. And just like we said, it looks like it only has one x-intercept. Now, although that looks very close to 4, it looks like it's a little bit before 4. If we do second calc and 0, it's going to ask us for a left bound. That is to the left, so that's okay. And then we've got to arrow quite a ways over to get to the right of that intersection. But there we are to the right. We'll hit enter and an extra time for the guess because we don't really care about the guess. And we can see that that x-intercept is happening at approximately 3.82. So we would say that the only real zero is that x is approximately 3.82. Next, we're asked, what is a quartic function with only 2 unique zeros? Those unique zeros being x equals -4 and x equals -6. Okay, if there are only 2 unique zeros, that means that's it. Those are the only 2 roots. There aren't any imaginary roots and there aren't any other real zeros. So if this is supposed to be a quartic function and we only have 2 real roots, we've somehow got to get 4 factors out of these 2 real roots. Well, if we just start writing, we might say f of x equals x plus 4 times x plus 6 to turn each of those roots into a factor. But we look at that and we're like, wait, that's only quadratic and we need quartic. Well, we have some options. If each of these factors had a multiplicity of 2, that would give us a quartic function. But that's not the only option. Maybe with those same 2 factors, the only multiplicity occurs on the x plus 6. That still would be quartic because we have 3, a multiplicity of 3 on the last one, a multiplicity of 1 on the first one, that still adds up to 4. Or maybe we have the function where the x plus 4 takes the multiplicity of 3. Now, if this was a test, you wouldn't need to give me all 3 of those answers. You would just need to give me one. But I would have all 3 on my answer key because any of them is an acceptable way to write a function with those 2 unique zeros. We're also asked if this function is even, odd, or neither, and to think about it from a graphical perspective. Well, that's kind of interesting. Let's actually pop each of those into our graphing calculator and take a look. So putting each of those equations into y equals, but each in a different slot and with a different color, we can just take a quick glance at each of them at the same time. I'm leaving it on a standard window like I had for my last problem. There's the blue one, kind of the expected W, nice and even. The pink one comes in with a kind of a lopsided approach, and then the gray one comes in with another lopsided approach. Now, at a quick glance, we can tell This is neither even nor odd. None of these are symmetrical to the y-axis, and none of them have point symmetry around the origin. But let's actually zoom in for just a minute because we can have an interesting conversation about them. I'm going to leave it at -10, but I'm going to take the x max just to 0 so that we can focus just on that part of the graph. Notice when you look at that, one of them bounces off the x-axis at -4 and -6. The second one, the pink one, has what I would call a wiggle at the axis at -6 and then just comes up one time through x equal to -4. So it has kind of that lopsided high and low dip there. And then the gray one is almost the mirror image of that, where the dip is happening right after -6 and the little wiggle happens on -4. That kind of makes sense if you think of the whole linear factor versus cubic factor thing. To show you what I mean, let's go in. I'm going to turn off all but the pink one so we can just focus on one of them. And then I'm going to snip that and put that image right into our graph so that we can talk about it. Okay, notice when we take a look at this one, this has the wiggle at -6 and the crossing at -4. It's because it's this graph right here. When I look at it, the cubic part has to take place at the -6, whereas the linear part, the part that sort of just passes through it one direction, has to take place at the -4. So even though all three of these were quartic functions working off of the same zeros, they all had up and up end behavior, they had some pretty distinct differences in the way their graphs worked because of where we put the powers.